Okay, this is a video on section 7.4, the dual nature of the electron. So, as you know, the last video you looked at, you would have learned about Bohr's theory about the electron in the hydrogen atom. Physicists were mystified and intrigued by Bohr's theory. They wondered, why would the electron in the hydrogen atom have energy which is quantized? Or, rephrasing the question, why would the electron in a hydrogen atom only be at fixed distances from the nucleus? It wasn't until about 1924 when a gentleman by the name of Louis de Broglie provided a solution to this problem. De Broglie reasoned that if light was behaving like a wave and a particle, so from studying the photoelectric effect, we saw that light can behave like a wave and also like a particle, then perhaps electrons could also act like a wave and a particle at the same time. So according to de Broglie, an electron bound to the nucleus behaves like a standing wave. A standing wave can be generated by, say, like plucking a string on a guitar. I don't know if you've ever seen a guitar string being plucked. Then you would see a standing wave. And in this little space right here, I'll try to draw a picture of a standing wave. So, like, here's the two ends of the guitar string, in which the guitar string is actually like anchored down to something, and a standing wave would kind of look like this. We'll do the best we can to draw our standing wave. It could be better, could be worse. It's not too bad. So, in a standing wave, the wave is basically stationary because they don't really travel along the string itself. At some points on the string, what we have are called nodes. So this right here is a node. And at other points on the string, we have what are called antinodes. These are antinodes right there. So we have nodes, and we have antinodes. A node is an area of zero vibration, and an antinode is an area of maximum vibration. So as we were saying, we have the nodes, which is an area of zero vibration, and there should be a node here at the end and another node here at the end right there. And we have the antinodes, which are areas of maximum vibration. And so the greater the frequency of vibration of this wave, the shorter the wavelength of the standing wave is going to be, and the greater the number of nodes that you'll have, and the greater the number of antinodes, of course. Now, what our good friend de Broglie suggested is that since the electron could be a wave and or a particle, or you would need both models to describe it, he suggested that the electron in a hydrogen atom is a standing wave that basically fits on the circumference of a circle. Because remember, the electron is only certain distances from the nucleus, and it's traveling in a circular path around the nucleus, and so that standing wave sits on the circumference of a circle, which is what we are trying to show you here, okay, in this diagram. So, although not all parts of the standing wave are shown, there is the standing wave that is existing on the circumference of this circle. So, if it's behaving like a standing wave, is traveling in a circular path, has to fit on the circumference of this circle. Otherwise, if the wave did not fit on the circumference of the circle, like in this diagram right here, it would begin to partially cancel itself out. And so each successive orbit of the electron as it travels would cancel out the wave more and more and more, and finally the amplitude of that standing wave would approach zero. So basically the electron would annihilate itself. And so the relationship between the circumference of the circle allowed, which is 2 pi r right there, right, and the wavelength lambda is given by this equation. So as we were saying, the relationship between the circumference of an allowed orbit, which is 2 pi r, the circumference of a circle, and the wavelength lambda of the electron is given by this equation in which we placed lines underneath, where r is the radius of the orbit, lambda is the wavelength of the electron, and n has the values of 1, 2, 3, etc. So n is a positive integer. Because n is a positive integer, it follows that r can only have certain values as n increases from 1 to 2 to 3 and so on. And because the energy of the electron depends on the size of the orbit, it must follow that the energy of the electron is quantized. So basically, the only way that the electron can exist at those certain distances is because it is a wave, not a particle traveling in a circular path around the nucleus, but a wave on a circular path. And it has to fit on the circumference of a specific circle, which can only be whole number multiples of its wavelength. Now, de Broglie also determined that he can find the wavelength of this particular particle, and that the wavelength of this particle was equal to h, the Planck's constant, divided by m, its mass, over u, its velocity. It turns out that this equation can be applied to anything, any subatomic particles that are in motion, or even non-subatomic particles. Anything with a motion, anything at all. You, a car, a ball, anything. According to what Broglie is saying, anything and everything should have a wavelength as it's moving. Pretty interesting. Pretty interesting idea to think that anything can have a wavelength. So, my friends, what about wavelengths of objects? Are they important? Are they not important? What's the deal? Well, I'm going to clean up the board a little bit here. And in your books, on page 292, there's a problem where it asks you to calculate the wavelength of a couple of different things. First is a tennis ball traveling at 150 miles per hour, which is reasonable for a professional tennis player's serve, which is 68 meters per second. So if we use this equation right here, whoops, hate when I do that. If we use this equation here, if we take the mass of the tennis ball in kilograms, the speed of the tennis ball in meters per second, which 150 miles per hour turns out to be 68 meters per second. And if we take the mass of this particular tennis ball, the tennis ball has a mass of about 6 times 10 to the negative 2 kilograms. If we plug all those numbers in, we'll get a wavelength for a tennis ball with a mass of 6.0 times 10 to the negative 2 kilograms, traveling at 68 meters per second. Its wavelength turns out to be 1.6 times 10 to the negative 34th meters. Yes, that's a 34. This weekend I'm buying a stylus, I promise. And if we did the same thing for an electron, traveling at the same speed, not traveling at the same speed. If we did the same thing for an electron, oh yes, traveling at the same speed. So let's take an electron traveling at the same speed, only now the mass of an electron is 9.1094 times 10 to the negative 31st kilograms. The wavelength for that electron traveling at that same speed turns out to be 1.1 times 10 to the negative 5th meters. So we see that the wavelength for a tennis ball traveling at that speed is incredibly small. And so the wavelength of this tennis ball is basically really unobservable. We basically do not and are not able to really see or anyway observe wave characteristics of very, very large objects like tennis balls, because their wave characteristics are so minimal, so tiny, they're basically negligible. Whereas the wave characteristics of really small particles, like electrons, well, that's significant, and you can see that that is significant. So you can see it because it's 1.1 times 10 to the negative 5th, which basically my understanding is that it is in the infrared range. So that's part of the infrared spectrum, or it's in the infrared spectrum. So it has the same wavelength as infrared light. And that's significant because it's observable. And electrons, even traveling at 68 meters per second, have wavelengths which are definitely measurable, definitely observable, and definitely have an effect on how the electron behaves. Okay, that's the end of this video. And if you have any questions, see me or Mr. Walsh tomorrow in class. Bye.